Look at the circulatory changes that occur during exercise. First and foremost, what I want you to realize and understand is that for exercise to be effective, we need to increase blood flow, primarily to the skeletal and cardiac muscles. And this process relies on several different events that can occur. For starters, by increasing cardiac output, we will cause an increase in the total amount of blood that is moving through the circulatory system every minute, which will naturally then increase the amount of blood flow that is going to the circulatory or to the skeletal and cardiac muscles. But we also are going to get some metabolic vasodilation, and I want to remind you what that means. From a previous slide, we took a look at this metabolic vasodilation, and I'm going to go ahead and include the paracrine signaling as well in this process. You're going to remember that of the paracrine signals, the ones that I wanted, let's move this over, so we're going to put this right here. Of the signals that I wanted you to know, for the paracrine signaling molecules, the most important was the chemical signal nitrous oxide. Nitric oxide. And so for nitric oxide, what that is a vasodilator. That's its primary function. And so consequently, if the amounts of nitric oxide in the localized area go up, then we're going to get vasodilation. So that would be a paracrine signaling molecule released by primarily the endothelial cells of the blood vessels. But in addition to nitric oxide, if we were to see an increase in CO2, that will result in an increase in the concentration of hydrogen ion in the circulatory system as well. And consequently, the pH of the system is going to go down. Now what I'm going to do, I'm going to kind of add a little bit of room in here because I want to go in and add some arrows, up and down arrows here in a second. So pH is going to change. And all of those are going to be metabolic vasodilators. Metabolic because the metabolism of the muscle, cellular respiration is causing these changes. So let's flip in here and see if I can remember how to find my arrows really quickly, or actually we're just going to go here and use my up arrows. So we're going to put nitric oxide increases. That's a really big arrow. So nitric oxide increases, CO2 increases, hydrogen ion increases. Okay. So CO2 increases, and we probably should put some more space right here so we can use my arrows a little bit better. I'll find another way, a better way to do this one day, not today. And so my carbon dioxide is going to go up, my hydrogen ion is going to go up, and guess what goes down? When hydrogen ion goes up, my pH goes down. So we'll go ahead and just turn that one around, and you can see then that relationship that exists despite my sloppy arrow work. It's better than the scribbles that I've been doing, but it's still not a perfect solution. So, oh well, we'll live with it. All right. So, moving my arrows there, this is how the relationship works. Okay. Now then the other thing that I'm going to add to this process, let's move the whole shebang up so I have a little bit more room, is oxygen. Okay, well, when oxygen goes down, we also get vasodilation. So these are the main processes that are going to be responsible for causing my vasodilation. This is my metabolic factors, okay? And so we'll put my down arrow right here. It's the basic strategy. And then in addition to all of this occurring in the skeletal muscles and in the cardiac muscles that I happen to be using, we're also going to divert, and that's kind of critical to get that idea in your head too. We're going to divert the blood away from the digestive system and the skin and probably some other things like kidneys and such, because when the working muscles are working, they already use such a tremendous amount of the blood supply anyway. When the muscles are working, that goes up substantially. And so things like skin become less important, less relevant at that particular time. So massive vasodilation for blood vessels supplying the heart and the skeletal muscles, whereas vasoconstriction for the gastrointestinal tract, the skin, and some of the other organs. This is kind of cool to me. Cardiac output can increase as much as 5 times, okay? Primarily due to rate. Contractility is also going to change, and you'll remember that contractility is part of the stroke volume. So as my stroke volume goes up, it's partly due because to my heart contracting more, it's partly due to my venous return, and it's going to therefore, so here's my contractility here. I don't know why I'm highlighting all the things in bold. They're already in bold, but hey, I'm kind of highlighter happy today. And then my ejection fraction. If you remember my definition for ejection fraction, that is going to be the percentage of the volume of the heart that is ejected during one contraction. And so ejection fraction, so you know, imagine then we never really get to 100% ever, but we might fluctuate between, say, 60% and, I don't know, 80, 90% type of fluctuations. And so that dictates how much blood is essentially exiting from the heart into the aorta and the pulmonary arteries. This diagram is a very lovely and an important diagram, and I really want you to study it. And you should be able to use this diagram to kind of put together a humongous concept map that is going to involve all of the different factors that affect the cardiovascular system. What we're doing is we're taking each of these and we're examining little pieces of the puzzle, and we examine those puzzle pieces closely. And I try to help you put the puzzle pieces together, but a lot of this work, you need to be assembling that at home. And there's really no better way to do that than drawing these giant concept maps to put it all together. A concept map is something like this, by the way. So, increased cardiac output increases blood flow to the skeletal muscles, and that's perfect, that makes sense. To increase my cardiac output, I'm going to have to increase my cardiac rate. And I can do this through activation of my sympathetic nerves or the release of epinephrine from my adrenal system. So we're going to combine that into this fancy dancy word and call it the sympathoadrenal system. That does not roll off the tongue very well, but that's basically what it means. Sympathetic nerves, activation of the adrenal gland. Don't forget that the sympathetic nervous system actually activates the adrenal medulla to release epinephrine, so it goes together. In addition to heart rate, my sympathetic nervous system will increase my stroke volume by increasing my contractility. And then we're working, right? So we're breathing deeper, our skeletal muscles are activated. Those are going to increase my venous return, which will also increase my stroke volume by causing that ventricle to stretch out, which lengthens those ventricle muscle fibers. Go back to your Frank Starling law of the heart and look at that. As those muscle fibers lengthen, the force of contraction increases and diastolic volume goes up. So this is an important connection that you need to remember. Most of that is through the skeletal muscle pump. I tend to group breathing in with that skeletal muscle pump because the diaphragm and the intercostals are all skeletal muscles. This particular figure breaks them apart, but when I draw this on the board, I usually put those two together as if they were one thing. And then I mentioned, and you should know, that the veins do have smooth muscle. And so because they have smooth muscle, they can also respond to the sympathetic nervous system activation, which will cause constriction of those smooth muscles, which will then constrict the diameter, reduce the diameter of the veins, and that actually causes the veins to, remember, the veins are my reservoir, my volume reservoir, so they expand to accommodate the volume of blood. When you constrict those, you're getting rid of that expansion and you're pushing the blood back into the arteries via the heart. So that's going to control your cardiac output. Now we're going to look at my blood flow to the muscles, right? Cardiac output's going to affect it, but then we also have constriction from the sympathetic nervous system of the viscera and skin. Go ahead and write skin down underneath this as well, because that's part of the process. We have dilation of the blood vessels in the skeletal muscle and cardiac muscle. This is skeletal, and so that's going to increase blood flow. And that dilation is due to the increase in muscle activity. More cellular respiration means more CO2, less oxygen, more acid. And then we also have the release of that nitric oxide. And so all of those together will factor into here. Skeletal muscle activity increases my venous return. And especially that nitric oxide, if it reaches the heart, it will also affect dilation of the blood vessels in the heart, and ultimately will end up affecting stroke volume. But the same is true with these other vasodilators. Okay, so put that big picture together, learn it, understand it, love it. It's going to really help you going